My name is Léon Victor, and I'm a PhD student at the University of Lyon in France. In this paper, I will present some work I've done with Alexandre, Meyer, and Saida Bouakaz, and it's entitled Learning-Based Pose Edition for Efficient and Interactive Design. Seems like it's changing. Okay, I can click. So first, for some contexts of the problem we're trying to solve. When we are editing motion for virtual characters, we can pick between two main families of approaches. If we choose to go the handmade route, we have the motion can be created step by step by posing the character skeleton at different timestamps. The computer is then tasked to fill in the gaps. This workflow yields precise results, which are true to the author's vision. And on the other hand, the whole process is quite time-consuming. On top of that, character motion is a complex behavior, so creating realistic animation will require knowledge in areas such as anatomy, muscle dynamics, and balance physics on the end of the animator. So this means that an inexperienced user trying to draw animation this way can easily look weird, and the results will fall in the realm of the uncanny valley. On the other side of the spectrum, there is motion capture. It is conceptually simpler. We put an actor in a recording studio, ask him or her to do some things. Then we record the motion and apply it directly to virtual characters. The advantage is that we get realism basically for free, but it is still quite expensive in terms of time and labor when looking for specific actions. And in any case, with any of those methods, even if the technology keeps getting better and we are providing better tools to our animators, there are still a human person that needs to be present to look over the resulting animation, clean it up, tweak it to fit some any kind of requirement they may have. In this work, we are focusing on poses as single frames in a character's motion. So a single pose might sound simple, but there are actually a lot of constraints dictating whether a pose will look good or not. Some are quite evident, such as is the character's anatomy respected, or is bone length constant, or is there interpenetration of his limbs, or are his articulations bending in impossible ways? But many others are more subtle, asking questions such as, is the character in balance, or does this pose reflect the character's goal or his personality? And here again, creating a good pose and respecting those constraints requires experience and knowledge on the artist's part. The way those constraints are usually handled is by, in animation software, is by using rigs. We call rigs pieces of software that we use to manipulate the skeleton, like handles and stuff like that, that we can use to restrict the motion of the skeleton underlying the mesh. And the animator can then manipulate the rigs to manipulate the motion. And here again, the limitations are the same because the constraints are set manually. So doing it right is difficult. There's also no way to handle the subtle constraints I just mentioned. So they will need to be handled empirically during the animation process. With this paper, we propose our solution, which is learning-based pose edition. So we propose to bridge the gap, kind of, between keyframe and mocap animation. We use neural network to learn the implicit skeleton constraints, and then we use this knowledge in a pose edition tool. The main advantage is that the user no longer has to have insights on all the complex skeleton constraints that I just described, because they are now learned implicitly from ground truth data. We also design our tool to fit in existing workflows. The idea is to avoid forcing results on the animator, but rather let him handle the process as he likes. Like he could toggle between our tool and other traditional ones as he wants. So for some related work, a lot of work has been dedicated to improving the posing process. The common idea that is mainly used is that we consider the skeleton as a puppet, and we leverage inverse kinematics to allow the users to manipulate the skeleton as a puppet. These IK solvers are mostly used to enforce the bond length constraint. Sorry, something is flashing on my screen. Sorry. No, I need to go back. Okay. Yeah. So the IK solvers are mostly used to enforce the bond length constraints. They take a starting pose as an input and then modify the skeleton to reach some targets while keeping the same distances between the joints. These methods distinguish themselves with the underlying optimization methods that are used. They have various upside and downsides in terms of speed and accuracy, but they share a common characteristic, is that they, in order to enforce other constraints, in particular joint rotation limits, again, we need to manually specify the maximum angles for each joint of the skeleton. Another subset of the work on position has taken interest in extracting information from ground truth data to generate plausible poses. So that's closer to what we are trying to achieve. So multiple solutions have been proposed. They each have their own limitations. In some cases, the generation is too slow to run in real time. So the manipulation is not that practical for the user. And or in some others, the example poses need to be kept in memory, at least partially. And we would like to avoid that to leave the memory available for other processes. So to finish up on the pose edition concepts, some other works stray away from the traditional puppeteering analogy and explore other ways to manipulate the pose. So those are some examples. In the first one, they use another concept of traditional undrawn animation, which is the line of action, which the artist can draw, and then they feed the skeleton and the pose to this line of action. Or in the second one, they're using users' hand motion in VR to tracking the hands motion and then translate that into a character animation. If we turn to actual animation synthesis, so we've seen a little bit of that earlier. So neural networks have received a lot of interest. A large body of work propose solutions to generate new motion in various contexts. These work are often supervised with, from high-level signals, and the synthesis is conditioned on this signal provided by a user, such as this is an example with the trajectory of that a locomotion animation should follow. And the other one, it's the text that a fashion animation should enunciate. And there's another part that is unsupervised, that is aiming to generate varied and random follow-up to an input animation, and also some work that are trying to fill the gaps between motion clips, for example. An important drawback, at least from our pose point of view, is that these work heavily rely on the temporal context of the animation, to which we don't have access when we are considering individual poses. So this leads me to the proposed method. So at the high level, our system can be assimilated to a traditional inverse kinematic solver, because it takes a starting pose and some desired joint positions as inputs, and it outputs a solved pose with the skeleton reaching for the targets. The twist is that the solver is actually a neural network trained on a dataset of ground truth pose data. This has multiple advantages. Yet again, the skeleton constraints are implicitly learned. And also a part of the heavy computation is delegated to a separate training phase. So generating a pose once the network is trained requires a single run through a few matrix multiplications, which is actually quite fast. On top of that, the learned network, as all neural networks, do not need to keep any data in memory. So this makes our method quite lightweight. So for the source of our data, we are fortunate, and in our field, animation is fairly available for research. So our pose dataset is built by joining together multiple existing motion capture datasets. We take all the clips from the other datasets, we retarget the skeletons to a common one, and then when training, we just sample single poses from these clips. As input to our networks, we use a simple skeleton representation, which is a simple vector of representing the joints position in space concatenated. So for 21 joint skeleton, it's our input is a single 63 values vector. So this figure represents the inner working of our method. You can see that we use 2.5 model. First, that we can train separately. First, we use an autoencoder to build a latent representation of the pose space, and then a solver network, which operates on this latent space to solve the given target position constraints. At runtime, an initial pose is fed to the autoencoder, and then the output vector is concatenated with the target positions. Yeah. So the autoencoder is an out-of-the-box one, quite traditional. It's trained to map a pose to and from a latent space, which is going to be built during the training. So the encoder decides where it puts its samples, and then the decoder learns to decode them. In our framework, the autoencoder serves two purposes. First, it speeds up the solver because it will have to work on fewer dimensions. And then secondly, it will allow us to project back incoherent results back to the pose space. As the decoder is trained to turn any latent point it is shown to a plausible pose, we ensure that any pose generated is comparable to a ground truth one. As I said, we can train the network separately. So we first train the autoencoder, and then, the autoencoder is trained using a standard mean square error for the reconstruction, and then for the solver, I'll talk about that right now. So the solver network works on the latent space only. It takes an encoded pose concatenated with target's joints positions and generates a new encoded pose, which, when decoded, will satisfy the constraints, so have its effector reaching for the targets. An instance of the solver is trained to solve a specific set of targets, so that the input vector is always the same dimension. I will talk a little bit later about how we can manage changing targets during a real workflow, and why I use the word instance. During training, instead of drawing random points to serve as targets, we sample effector's position from the source clip of the input. So we take another pose from the same input clip, and then take the second pose joins, like for example the ends position, and then use that position as a target for our solver. In this way, we ensure that we are learning from realistic targets and never from impossible ones. For the solver network's cost function, it is trained to minimize a custom loss, which is designed to reflect its high-level objective. So we want the result pose to reach the targets, but we also want it to be similar to the input, because the the resulting pose still needs to be close to the input one, otherwise it wouldn't work. So to reflect that, our loss function is composed of two terms. On the left, in pink, we compute the distance between the target joints in the resulting pose and the target positions. And on the right, in green, we compute the difference between the positions of all the other joints in the starting pose and the generated pose. The second term is weighted by a constant to give more or less importance to either of them. In our experiments, the left term is valued 10 times more than the right, but it's not fixed. Another impact of this function is that the output will prioritize balancing both terms rather than reaching zero on one of them. In effect, this means that targets are not rules, but rather guides. And I will show some examples on how this translates. For the actual networks architecture, they are pretty simple. As I mentioned earlier, our pose data is low dimensional with only 63 values and no temporal data. And thanks to this property, our models can be simple and we do not require modern architectures or complex things. In our examples, we use simple multi-layer perceptrons with 3 layers and 126 units per layer. And yeah, our experiments show that they are sufficient. It's quite possible that bigger and more complex architectures could better model the skeleton intricacies and yield better results, but using such models will lead to a loss of performance at inference time. Because in addition of being simple, these models come with the advantage of being pretty fast to train. For an indication, training both models until satisfying results on my average computer took less than an hour during our experiments. And in the same way, once trained, inference can be executed in very short times. So those are results in real time. In this example, I'm manipulating the skeleton by moving around some targets, which are associated with the ends using a mouse. The targets are shown in red, and in yellow is when I'm clicking them and then manipulating them. We can see that the skeleton reaches for the targets and that its whole body moves to adapt the pose. Yeah. We are respecting the implicit constraints. And once again, I haven't manually set them anywhere. The limb lengths are constant. There is no self-occlusion or interpenetrations. And overall, the generated pose feel natural. As a comparison, and to highlight the advantages of the learned constraints, there are some side-by-side comparisons with a traditional IK solver. So we're using the fabric algorithm and we are cheating a bit because I haven't set any constraints either on fabric, but it illustrates quite well that on the left, our method keeps generating appealing poses, while the fabric quickly loses the track of the skeleton and starts producing unrealistic poses. A little bit more about what we can see. You can see that the torso is twisted to keep up with the targets, and also that the legs to mimic maintaining balance. So in cases where more targets are needed at the same time, it is possible to run multiple solvers in sequence. This allows us to reuse previously trained solvers instead of training a new one for each separate situation. The sequence solver also takes advantage of the separate autoencoder and solver. We need to encode the initial pose once and then roll all the solvers in sequence, then decode the results. And this way we save both time and compute. For the same results with multiple solvers. In this example, I have 3 solvers, one for the 2 hands another one for the head, and then one for the two ankles. We can also, in this example, see that it works quite well. And also it illustrates the fact that targets are not set in stone. They are more like guides. We can see that the head target in particular is interpreted by the network as an indication to tilt the torso rather than completely turn around to meet the target precisely.
We are a bit cautious about time. Can you summarize your work in next few slides? Yeah.
I will skip the next one. Sorry for the time. So yeah. So we propose a new neural network-based method for pose edition, which learns complex skeleton constraints from the data. And that's what I skipped, but it's fast, lightweight, and easy to set up and use. The limitations are common with most data-driven based methods. The quality of the result is strongly tied to the quality and size of the training data sets. In future work, we will work on validating this method through usability experiments in order to study and quantify how the system could integrate with and improve an animator's workflow. And also future work will focus on extending this method to translate to other skeleton topologies than the standard one we have here. All right, I'm done. Thank you for your attention. And if you have any questions, I'm happy to answer them.
That's great. I believe Professor Daniel has a question to ask.
Yes, yes, I have a question. Yes, in your paper you had one of the reviewer who mentioned that the method, they are not only this kind of method, but you have other methods, like for example the line of action. You have added, I saw in the new version of the paper or the journal, and also in your slide, the line of action. But what I find is that you didn't try to compare and to see the advantage of your method compared to the line of action, for example. You only compare to different IK methods, but what is the advantage of your approach compared, for example, to the line of action?
So in my point of view, sorry, I don't have the video, so. In my point of view, they are actually quite different because our method is designed to fit in existing pipelines and to not to reinvent another method completely. Like it's supposed to fit in the workflow animators are currently using. So that's why we are comparing only with IK methods, because they are comparable and actually used. And yeah, I think the line of action is great work, but it's not, it doesn't fit as nicely in the existing workflow as ours.
But for example, if you try to extend this to something not only pose, but to in a complete animation, do you think that your method is better?
Well, it's quite different.
Yes, it's different.
At the moment, it's not designed to work with animations.
I agree, it's different. I just try, not just because it was addressed by the reviewer, is that what I just would like to know is more than, not to look at the strict comparison, is more to see the globally the advantage. If you think, if you can tell me really it's much better with our approach, not only your approach, the other IK approach, but is it, I just don't see the really a strong argument for this kind of method. I try to find one.
We will have to actually put animators in front of both methods and then compare how they liked each of them. I'm not really sure we can have a precise comparison of both if not made by users. But that's actually.
It's not a big critics. It's just that I was.
No,
I saw that it's in some way it would be better if you had not only mentioned the paper, but try to just put some arguments saying it's different or it's there is an advantage in mind or something. Nothing, just mentioned. There are other works, but I just find this a little weak, but it's okay.
Yeah.
Okay. So I think there will be more questions coming through. I saw people has raising their hands. So so we will let Eric to ask a question and then phone, and then afterward we'll have to move on to the next one. So just for note, so that for both question and answers, please keep it concise, just because cautious we might running a bit late for the session. So yeah. So go ahead, Eric.
Yeah, hi. Thanks for the very nice presentation. I was wondering, like posing, to me, it seems like it really depends on the intended motion. And in your case, I feel that you're doing it like as if it was not really static, but you're not considering what will happen in the future and the past. Could you comment on that a little bit?
I'm not sure I got the question quite right, but yeah, no.
Well, it depends on if you want to have like a static stance, or if you're in the middle of a jump. It's quite different, even though your end effectors in an I key manner are the same. The whole body, it's different from maintaining balance when you're standing or when you're in the middle of a jump, right?
But well, it's actually an interesting question, because it would be possible to consider temporal context. I mentioned in the talk that we made the choice not to consider it, because we want our tool to be used in any context. But it might be a good idea to train our model with specific extracted motion, like using only poses extracted from motion capture clips of someone jumping, and then train only our method on the pose extracted from that, so that then the solver will only generate this kind of pose. But yeah, we made the choice not to have any temporal context in here.
Okay, thank you.
Phone,
yeah, okay. Okay, it will be very, very short questions. I know we're really late. Okay, my question regarding the, you are using autoencoder. So my question is, what happened? What's your real motivation behind using the autoencoder if the dimension of the pose is not that big? And what happened if you don't use autoencoder for your network?
Actually, I made some experiments not using the autoencoder. I will try to get back to the slides. I keep losing my mouse. No, sorry. So I can't show the slides. But I tried training the same model with the autoencoder kind of included in the network, like the solver with the autoencoder at once. And it worked as well, but the difference was that having both pieces separated, we could train the solvers separately. We didn't have to retrain the autoencoder every time we wanted to switch targets. That was the main selling point. That way, like if someone needs to have a solver working on, I don't know, the elbows or something, it could train only the solver network, which is like 1/3 of the network instead of the whole thing.
Okay, I got it. I think like you mean basically like you got the framework, you got it means kind of network has been trained. Therefore, if the people want to use it, they don't have to train the whole network, for the especially for.
Yeah, and training specific solvers is useful because we can pick whichever we want in any scenario. Once we have one network trained for each joint, we can just mix them up and solve any constraints that the user might have. Like if we want to have all the joints fixed except for the head, we can just use all the solvers we have trained, and that's it. There's no retraining needed.